Okay, so welcome back to this next video in which we are discussing G-protein coupled receptors. Okay, right, so we have just looked at the structure of an alpha subunit of a heterotrimeric G-protein, and we've seen the important little domains that the heterotrimeric G-protein alpha subunit has. Okay, and this is going to become very important when we want to understand why binding to the G-protein coupled receptor actually causes the release of the guanosine diphosphate from the alpha subunit of the heterotrimeric G-protein. Okay, so we will use this structure later on. Okay, but for now we're going to go back to using our cruder structure, which was shown here, and we're going to show how, when the G-protein coupled receptor activates, how a heterotrimeric G-protein then binds to the G-protein coupled receptor. Okay, so let's start by drawing our activated G-protein coupled receptor here. So once again, here is the plasma membrane. Here now is our heterotrimeric, sorry, no, not our heterotrimeric G-protein, our G-protein coupled receptor. This is our 7 transmembrane bundle here. Okay, so we've got helix number 1 there, helix number 2 here, helix number 3, helix number 4, 5, and then 6 here. Okay, like so. I'll split it up. Right, and then I'll continue the plasma membrane on here. So here's the N-terminal here, and here's the C-terminal. And remember, the key conformational change that occurs when the ligand has bound to the G-protein coupled receptor is that now these intracellular portions of transmembrane helix number 5 and transmembrane helix number 6 are going to splay outwards like so and open up this crevice, and indeed our alpha subunit of our heterotrimeric G-protein is going to come and bind now in this crevice. Specifically, the C-terminal tail of the alpha subunit of the heterotrimeric G-protein is going to insert itself into this crevice and is going to interact with that arginine on helix number 3 at position number 50. Remember, that breaks that salt bridge. If I just go back to this picture. Okay, so the one that breaks this salt bridge here, and this arginine now is going to interact with the C-terminal tail of the alpha subunit of the heterotrimeric G-protein. Okay, right, so let's now draw our heterotrimeric G-protein on here. So again, we'll go back to showing the heterotrimeric G-protein as our cruder picture. So here is the GTPase domain. I've forgotten to show the little GDP binding site here, so I'll have to correct that now. So here's the GDP bound in that GDP binding site here. So there's the GDP in turquoise, and in red here, this is the guanine nucleotide binding site. Okay, let's then put on the helical domain beneath it here. Okay, which is then linked to the GTPase domain by linker number 1 here, and then by linker number 2, which then, remember, has that switch region number 1, okay, which we previously covered in orange here, so we'll stick to that. So here is switch region number 1, okay, which is very important in binding to the beta subunit. So that's switch 1. We'll also add on switch 2 here, again in orange, okay. And now let's put on the other important domains then of the alpha subunit of the heterotrimeric G-protein. So firstly, let's put on that amino terminal helix, okay, here, which will be interacting with the beta subunit, and it should have a lipid moiety attached into the plasma membrane. It will look a bit silly if I draw that there, because it will have to be extremely long, but in reality it would have a lipid moiety attaching this to the plasma membrane there. Okay. So I'll colour in the alpha N helix here in orange. So to label a few of these up, this is switch 2, this is alpha N. Then we've got that alpha N beta 1 motif here, which is going to be binding to the G-protein coupled receptor now that our G-protein coupled receptor is in this activated state. And I might just put a little label here for the G-protein coupled receptor, R star, the activated state of the G-protein coupled receptor. Okay, and then let's add on the other important domain. So here is the C-terminal tail of the alpha subunit of the heterotrimeric G protein that will be inserting into the crevice that is now open at the base of the G protein coupled receptor, and that's one of the key ways in which the alpha subunit of the heterotrimeric G protein binds to the G protein coupled receptor. Then to add on those other important domains, those two loops, remember. Okay, so one of these is the alpha 4 beta 6 loop, this one here. Okay, and the other is the alpha 3 beta 5 loop here. Okay, right, so they will also be binding to the underside of the activated G protein coupled receptor here. Okay, then let's put the beta and the gamma subunit on, because remember the beta and the gamma subunit are also important in binding to the G protein coupled receptor. Okay, and this has important consequences for specificity. Okay, so let's draw the 7-bladed beta propeller domain of the beta subunit of the G protein here. Okay, there we go. We'll have the center there, and here are the 7 blades. So 1, 2, 3, 4, 5, 6, and 7. And then you'll have the C-terminal portion here, which will also be binding to the G protein coupled receptor. So I'll colour it in purple here. Okay, then you also have the N-terminal portion of the beta subunit here. Okay, and I'll colour that helix in, I think I'll do it in green actually, I think I did it in green previously. So here is that N-terminal alpha helix of the beta subunit here. Okay, and then this will be binding to the gamma subunit, so let's put on the gamma subunit. So remember, the gamma subunit has an alpha helix, and they will, the alpha helix of the gamma subunit will form a coiled coil domain with the alpha helix of the beta subunit here. And then the gamma subunit will come up here, and again its C-terminal portion is going to be binding to the G protein coupled receptor, so I'll colour that in purple as well. Haven't quite shown it binding, but it should be binding to the G protein coupled receptor as well. Okay, so let's just then colour in this alpha helix of the gamma subunit in blue here. And here's the amino terminus. Right, so that's G gamma, this is G beta, and this is G alpha here. So here is the heterotrimeric G protein still currently with guanosine diphosphate bound to it, binding to the activated G protein coupled receptor. Okay, so now a boring word but a very important topic that we need to discuss is the topic of specificity. Okay, so what does this mean? This means that different G protein coupled receptors, when they are activated, they bind to and activate different heterotrimeric G proteins. Now this is common knowledge. We all know that certain G protein coupled receptors have a certain tendency to activate certain heterotrimeric G proteins. For instance, the beta-2 adrenergic receptor activates mainly GS heterotrimeric G proteins, i.e. G proteins where the alpha subunit is alpha S. Okay, so what determines the specificity of a G protein coupled receptor? Because what we've talked about here, you know, the G protein coupled receptor goes through pretty much the same conformational change, and then that allows the binding of the heterotrimeric G protein. So what determines specificity? Well, the answer is we don't actually have a very good understanding of that at all. Okay, so we don't understand what structural features of the G protein coupled receptor determine which heterotrimeric G proteins it binds. Okay, but it is important to remember that specificity is not just about the alpha subunit. People always talk about the alpha subunit because it is arguably the most important of the subunits of the heterotrimeric G proteins. Okay, but specificity doesn't just depend on the alpha subunit. It also depends on the beta and the gamma subunit, i.e. G protein coupled receptors can favour whole heterotrimeric G proteins, i.e. they look at the alpha, the beta and the gamma subunit and determine whether they want to bind to that or not. Okay, so it's not just the alpha subunit that determines whether a heterotrimeric G protein can bind to a certain activated G protein coupled receptor. To give you an example of that, let's take the example of the M2 receptor, okay, a muscarinic acetylcholine receptor. Basically, the M2 receptor can activate heterotrimeric G proteins of the GO type, where the alpha subunit is G alpha O. Okay, however, the beta and the gamma subunits do matter. So for instance, if we have the heterotrimeric G protein G alpha O beta 1 gamma 2, okay, so where you have the alpha subunit as the alpha O subunit, the beta subunit as the beta 1 subunit, and the gamma subunit as the gamma 2 subunit, the M2 receptor will not bind to this heterotrimeric G protein, okay, so no, basically it won't bind to that one. However, if you change that gamma subunit, okay, if you change the gamma subunit to either gamma 5 or gamma 7, then it will bind to it. Okay, so that's a demonstration that actually the beta and the gamma subunits do matter in determining whether a G protein coupled receptor will bind to a certain heterotrimeric G protein. People often say the beta gamma subunits don't matter, okay? It's a useful simplification that only the alpha subunit matters, but it's not true, okay? In reality, the beta and the gamma subunits do bind to the G protein coupled receptor, and they do influence whether a certain G protein coupled receptor will bind to that heterotrimeric G protein. So they do confer, they are involved in the specificity of which heterotrimeric G proteins a G protein coupled receptor will bind to. Okay, right. So that's the rant on the beta-gamma subunits being important done. Okay, I've said that we don't actually understand what underlies why some G protein coupled receptors activate certain heterotrimeric G proteins and other G protein coupled receptors activate completely different ones. We don't understand that. Okay, we will develop our understanding of that in years to come, surely. Okay, right, the other thing that I now want to add on to this is the concept of biased agonism, which we will come back to big time later on, okay, but I think it's appropriate to say something about biased agonism now, okay, whilst we're on the topic of specificity. Okay, so specificity is all about which heterotrimeric G proteins a G protein coupled receptor will activate. Okay, now at present, in the classical model of activation of G protein coupled receptors, we have said that the G protein coupled receptor has only two states. It has the inactive state where it doesn't bind to any heterotrimeric G proteins, and then it has the activated state where it can bind to certain heterotrimeric G proteins. Okay, and the two are in dynamic equilibrium and ligands can shift it from one to the other. Okay. Right, so at the moment our model is that once you're in this conformation, there are certain heterotrimeric G proteins that you will bind to and there are certain that you won't, okay? I.e. your specificity is set. However, it's more complicated than that. Basically, different ligands binding to the G protein coupled receptor can actually change the conformation of the G protein coupled receptor in slightly different ways, and this can change the specificity of the G protein coupled receptor. Okay, so for instance, let me give you an example because that's probably the easiest way to explain this. Let's take the type 1 cannabinoid receptor, which is again a rhodopsin family G protein coupled receptor. So CB1 here stands for type 1 cannabinoid receptor. Okay, so these are the targets, or one of the targets for the active ingredient of cannabis, delta-9 tetrahydrocannabinol. Okay, but you also have a great number of endocannabinoids, which are also ligands for type 1 cannabinoid receptors. Okay, right. Now, basically, you can stimulate the type 1 cannabinoid receptor with different ligands, okay, and then we're just going to call these arbitrarily ligand 1 and ligand 2. And basically, when ligand 1 binds to the type 1 cannabinoid receptor, it will cause a change in conformation in that type 1 cannabinoid receptor that then allows the type 1 cannabinoid receptor to activate heterotrimeric G proteins which have the alpha I1 or alpha I2 alpha subunits in them, okay? Whereas, when you activate it with ligand 2, this will activate the G protein coupled receptor to go into a conformation where it can activate heterotrimeric G proteins with the G alpha I3 alpha subunit in. So basically the idea here is that different ligands can bind to the G protein coupled receptor, the same G protein coupled receptor. They can cause different conformational changes, okay? So it's gone, this model's gone, where it's just one conformational change that all ligands cause, okay? And different ligands can cause different conformational changes in the G protein coupled receptor, and then these different conformations of the same G protein coupled receptor can then activate different heterotrimeric G proteins. Okay, so the specificity of the heterotrimeric G protein is determined by which ligand binds to it in certain cases. This is the emerging concept of biased agonism, and this is a paradigm shift in the field of G protein coupled receptors, away from this classical model towards this more correct model of G protein coupled receptors having many different conformations which can be induced by different ligands, and these different conformations then having different specificities for activating certain downstream pathways. Okay, and as I say, we will come back to this because this is starting to have clinical utility. Okay, so we will come back to this at the end, where we'll talk about drugs that are biased agonists of beta-1 adrenergic receptors and also mu-opioid receptors. Okay, right. So, the next thing we want to talk about, now that we've talked about the binding of the heterotrimeric G protein to the G protein coupled receptor, is the conformational change that now occurs in the alpha subunit that allows this guanosine diphosphate to be released. Okay, and this was the big reason that we actually looked at the structure of alpha subunits of heterotrimeric G proteins in this gory detail that we did. Okay, so let's now talk about the conformational changes that occur that helps to release the guanosine diphosphate from the alpha subunit of the heterotrimeric G protein. So the principal change that is thought to occur is that when the C-terminal domain here binds in the crevice of the G protein coupled receptor, that's believed to transmit translation, i.e. a movement along this alpha 5 helix here, which then transmits the movement to this alpha 5 beta 6 motif here, which is a key part of the guanine nucleotide binding domain. Okay, so through the C-terminal domain binding to the G protein coupled receptor, you get a change in conformation in this alpha 5 beta 6 portion, this alpha 5 beta 6 loop, which then causes changes in the guanine nucleotide binding domain. So that's one of the key ones. Okay, so I'll just, where should I put this? Right, I might outline this on here. Okay, so one, the C-terminal portion binds to the G protein coupled receptor. That causes a conformational change that's transmitted along the alpha 5 helix that then gets to the alpha 5 beta 6 loop, which of course is part of the guanine nucleotide binding domain. So there is one way that we get a conformational change in the guanine nucleotide binding domain. Okay, next we also have the alpha 4 beta 6 loop here binding to the G protein coupled receptor. This is believed to transmit conformational changes down this beta 6 loop, this beta 6 strand here, to the alpha 5 beta 6 loop down here, and again we get changes in conformation in that guanine nucleotide binding domain there. Okay, so this is alpha 4 beta 6 binds to the G protein coupled receptor, transmits the conformational change down the beta 6 strand, which then goes to the alpha 5 beta 6 loop. Okay, that also helps to bring about a conformational change in the guanine nucleotide binding domain. Okay, going back and having a look at another one, let's turn our attention to the alpha N beta 1 portion, this portion between alpha N and beta 1. This also binds to the G protein coupled receptor. Okay, it will then transmit a conformational change down the beta 1 strand to this P loop here, which is another important component of the guanine nucleotide binding pocket. The P loop and the alpha 5 beta 6 together form the guanine nucleotide binding pocket. Okay, right, so let's add that on. Okay, so alpha N beta 1 binds to the G protein coupled receptor. This transmits a conformational change down beta 1 to the P loop, and then of course that's part of the guanine nucleotide binding pocket as well. So there's another way we get a conformational change in the guanine nucleotide binding pocket. Finally, another important conformational change that's believed to aid the GDP coming out of that binding pocket there. Okay, what we just talked about is the distortions that might cause the GDP to become unbound, but now something that's believed to help the GDP then escape from this binding site and get out is that the helical domain is believed to drop down. Okay, and the reason this happens is because of a disruption in the binding between the switch-free region and this alpha D alpha E loop, which is why I drew your attention to this interaction earlier on. Okay, so when the alpha-free beta 5 loop here binds to the GPCR, that causes conformational changes that are transmitted down alpha-free to switch-free here. And therefore it now stops actually binding to the alpha-6 alpha E loop, and that actually causes the whole helical domain to fall a little bit, and that's believed to help the GDP that has become unbound because of the other conformational changes in escaping from this binding site and getting out now. Okay, so let's just add that on. Okay, so number 4 here, alpha-3 beta 5 moves because it's bound now to the GPCR. This is transmitted down alpha-3 to switch 1, okay, which then causes release of alpha D alpha E loop, which then causes the helical domain to drop down. Okay, and we'll go over onto another piece of paper and actually show these conformational changes now that have occurred, and we'll see how GTP is then going to bind and cause the release of the G beta gamma complex. Okay, right, so let's draw this picture again. So here is the membrane here, and again we'll draw our 7 helix bundle of the activated G protein coupled receptor here. Okay, like so. So here is the first membrane spanning alpha helix, the second, the third, the fourth, the fifth, the 6th and the 7th, like so. Okay, and it's sitting in the membrane here. Right, here's the N-terminus, here's the C-terminus of our G protein coupled receptor. Now let's draw our alpha subunit on, having undergone these conformational changes that we've just outlined. Okay, right, so once again, here is the GTPase domain with our guanine nucleotide binding site there, which is now vacant. There is no GDP bound there anymore. The GDP has gone. Okay, right. Then let's put on our helical domain here. The helical domain has now dropped down because of that lost interaction between switch 3 and the alpha D alpha E loop. Okay, so here is still linker 1, here is linker 2, here is that switch region 1 now, here is switch region 2. They're still bound at the moment to the G beta gamma subunit, or rather the beta subunit of the beta gamma complex. Okay, like so. There is linker 2 at the base there, so that's linker 1 here, linker 2 here. Let's colour in the helical domain once again in blue down here, that's dropped down, and that's thought to be helpful in allowing the GDP to actually escape. Okay, then let's draw the alpha N helix here, okay, which is still bound to the beta subunit. Okay, so I'll colour that in orange again here. Okay, and we'll forget the lipid moieties, although they still would be there in reality. Okay, here is this portion, the alpha and beta 1 portion that will be bound to our G protein coupled receptor. Here is the extremely important C-terminal domain, which is bound to the G protein coupled receptor. Okay, and then our 2 important loops here, which are also bound to the G protein coupled receptor. Okay, so here is alpha 3 beta 5 here. Okay, and this is alpha 4 beta 6 here. Okay, right, so let's colour those 2 in as well, like so. Right, okay, so we no longer have the GDP bound there, but the beta subunit is still at present bound to the alpha subunit. So let's draw the beta subunit bound here. Okay, so here is this seven-bladed beta propeller here. Okay, 1, 2, 3, 4, 5, 6, and 7. Okay, here is the C-terminal portion of the beta strand, which is still bound to our G protein coupled receptor up here. Okay, and then we'll draw on the N-terminal of our beta subunit, which will still be bound to our N-terminal portion of the gamma subunit by that coiled domain. So here's the alpha helix of the beta subunit. Here's the alpha helix of the gamma subunit in this coiled domain. And then here is the C-terminal of the gamma subunit, which again I'll try to show bound to the G protein coupled receptor up here. Okay, like so. And then here is the N-terminal alpha helix of the gamma subunit in that coiled domain, with N-terminal there. Right, okay, so there's where we've got to at the moment. So I'll stress again, everything's still bound together at the moment. We've lost the GDP, but the alpha N helix is still bound to our beta propeller of the G beta subunit, and so are switch 1 and switch 2 regions. Okay, the next important stage is what's going to happen is a GTP molecule is now going to come into that binding site and replace the GDP molecule. Okay, so in now comes a GTP molecule from the cytoplasm. So you have a much higher concentration of GTP in the cytoplasm than you do GDP. Okay, so in comes the GTP molecule here. And what colour should I colour the GTP in? I think I'll have it in yellow here. Okay, so this is GTP here now. And when the GTP comes in, that causes conformational changes in the switch region 1 and the switch region 2. So here's switch 1 and here's switch 2. Basically, switch region 1 and switch region 2, they now fold in. Okay, the additional phosphate on that guanine nucleotide here is going to cause switch 1 and switch 2 to fold in. Okay, so this folds in like so, and this folds in like so, and they basically close over the guanine nucleotide binding domain. Now that disrupts their interaction with the G beta subunit here. Okay, because basically now what's going to happen is they're going to have totally different residues available for binding to the G beta subunit. Okay, and this is quite striking basically. Initially, when they are normally in their normal conformation, okay, and they've formed this binding interface for binding to the G beta subunit, they have a huge number of hydrophobic residues facing the G beta subunit, which is how they bind to the G beta subunit. After this conformational change where they're folding inwards, the residues that are now facing the G beta subunit have gone from being hydrophobic to being charged. Okay, so you get loads of charged residues now facing the G beta subunit, and obviously charged and hydrophobic are completely opposite. So now what happens is the beta subunit now loses that really important interaction between itself and the alpha subunit. Okay, and you might say, but it's still got the alpha N helix here, but the alpha N helix interaction is really weak. It's the switch 1 and the switch 2 regions that are the main binding interface between the alpha subunit and the beta subunit. Okay, and now that the switch regions have undergone this conformational change, the beta subunit loses its ability to bind to the alpha subunit, and therefore it now cleaves away here. Okay, and takes the gamma subunit with it, because the gamma subunit wasn't even bound to the alpha subunit in the first place. Okay, and they cleave off the receptor as well. Their interaction with the receptor was quite weak. So once they've lost their interaction with the alpha subunit, they cleave off the receptor and they go off. However, they still remain attached to the membrane, of course, because they have the lipid moiety that's attached to the C-terminal tail of the gamma subunit. So they now go off. Okay, so off goes the G beta gamma complex here. Okay, right. Then let's talk about how the G alpha subunit is going to cleave off the activated G protein coupled receptor. So basically, when GTP binds to the guanine nucleotide binding site of the alpha subunit, what is thought to happen is the exact opposite conformational changes occur to the conformational changes that cause the GDP to be released. Okay, so basically, if you imagine this, when the G-alpha bound, okay, so when the G-alpha subunit bound to the GPCR, it caused a bunch of conformational changes that basically kicked out the guanosine diphosphate. Okay, so the GDP is bumped out, basically. I'll just put bumped out. Okay, now what's going to happen is that basically a stronger force is coming in here. The guanosine triphosphate has come in here, and basically it's as though it pulls everything back. It pulls all of these things back, and then pulls them off the G protein coupled receptor. So now GTP comes in and binds, okay, and that basically bumps the G protein coupled receptor off. Okay, so GPCR is now bumped off, and that cleaves the alpha subunit off the G protein coupled receptor, and again it now goes off on its own, basically. Okay, and it again will remain attached to the underside of the phospholipid bilayer by the lipid moiety that's attached to the amino terminal end of the alpha subunit. Okay, right. So now both of these molecules that we formed, the alpha subunit which has GTP bound to it, which people often denote G-alpha GTP, okay, the on-state alpha subunit and the G-beta gamma complex, they both go off to have signaling roles. They both go off to bind to other signaling molecules and have effects, basically. Okay, signaling. Right. The final thing that I want to mention here is something about the kinetics of this process. Okay, so another boring word, kinetics, but it is again a very important point, and it's again a great open question that we don't currently know the answer to. Basically, let me show you some extreme statistics here. Okay, rhodopsin, the rhodopsin receptor, which activates transducin heterotrimeric G proteins. So remember, heterotrimeric G proteins where the alpha subunit is either G-alpha T1 or G-alpha T2. Okay, these actually activate 200 heterotrimeric G proteins a second, GT, per second. Okay, so I should have stressed this point more. Once the heterotrimeric G protein is cleaved off, both the beta gamma complex and the alpha subunit, the G protein coupled receptor can now bind another inactive heterotrimeric G protein and activate that. Okay, and in fact, rhodopsin receptors, once activated, activate 200 transducin heterotrimeric G proteins a second. Okay, contrast that to the adenosine 2A adenosine receptor, and also the beta 2 adrenoreceptor, which really have a rate of around 2 GS subunits per second. So they activate heterotrimeric G proteins where the alpha subunit is G-alpha S. Okay, so this obviously is a huge kinetics difference here, a huge difference in the rate at which this reaction actually occurs for the rhodopsin receptor and the adenosine 2A adenosine receptor and beta 2 adrenoreceptor. Okay, so this is obviously a very important phenomenon that must have a reason for why the rhodopsin receptor is so much quicker at doing this process of actually activating the heterotrimeric G protein. Okay, but we don't know why the rhodopsin receptor is so much better at doing it. Maybe it's a difference in the heterotrimeric G protein. Okay, but at present the reason for why rhodopsin is so fast and these two are so slow isn't understood, but that is an important point, that there is different speeds here. And the other important point is that once a heterotrimeric G protein has been activated and has cleaved off the activated G protein coupled receptor, that the G protein coupled receptor can then bind other inactive heterotrimeric G proteins and activate them. Okay, right. So in the next video, what we'll talk about is the regulators of G protein signaling proteins, okay, and then we'll move on to looking at receptor dimerization.